So there's two schools of thought on how you can build a flip-flop with an enable input. The first and sort of the most obvious approach is to what's called gate the clock line, where you add an AND gate here. So the clock line is only high, at least as far as from the flip-flop's perspective, as long as the enable pin is also high. The other alternative is you hook the clock line directly into the flip-flop, and then you select between what device gets to write to the flip-flop on the next positive rising edge. Either the old value of Q loops back, or you have an input that overrides it and is fed through a multiplexer. So let's compare these two approaches. So the first approach on the left here is sort of the desired approach because it gets us the effect that we wanted. The clock line is toggling, it just keeps copying Q into the input. If the input high is low, and we toggle the clock line, again, nothing happens. And if the enable is high, it will copy in to Q. So on the positive clock edge, Q is copied in. And toggling the clock, obviously there's nothing because the input's still copied in. And then when the enable pin goes low, we will continue to store the value of Q by just continuing to feed it from the output back into the input. So by having the input line high as the clock is toggled, absolutely nothing happens. And the data is copied precisely on the next positive clock edge. So I can play with the enable line while the clock line is low, and even though that affects what's going into D, the output doesn't change until the next positive clock edge, which is precisely what we want from synchronous circuits. We want everything to change or update on the positive clock edge. This solution here, by gating the clock, even though you could argue it's a lot less hardware and it's cheaper, a single AND gate is simpler than a multiplexer, it doesn't have that desired effect. And here's why. If you have the data, if the enable line is high, input data is high, on the next positive clock edge, then Q will react exactly how you expect. But the problem is that the AND of the enable line and the clock line here acts essentially like a phantom clock line to the flip-flop, and will react to positive edges of that phantom line, whether it's the actual clock or the enable pin that changes. So for instance, if the enable pin is low, clock line goes low, input goes low, everything's fine, this is reacting as it should be. If the clock line goes high first, then if the enable pin goes high afterwards, we shouldn't see anything happen because the positive edge has already occurred. We see that in the first design, right? Clock goes positive, nothing happens. But here, if we turn on the enable pin, that will cause a rising edge from the output of the AND gate, and the output here, Q, changes even though the clock line didn't change. So this fails to be a circuit that's perfectly in sync with the clock line because it can change on the state change of the enable line rather than the clock line. Another problem is that the update is not perfect in that the gate will also present a minor amount of delay. So we can edit the circuit, hook the clock lines together, and simulate this in single step mode, which will now simulate the delay of these circuits. If the input is high for both, and we sort of wait a while for the input to propagate through, then as soon, the absolute moment the clock line goes high, the flip-flops should transition as fast as possible. So here, the clock line goes high, we have the delay of the flip-flop, and I have to actually put the enable line on. So put the enable line on for both. So now if the clock line rises, for the first flip-flop, this changes as quickly as one flip-flop can update. For the second flip-flop, this signal has to go through the propagation delay of the AND gate first. So this means that the second flip-flop will update ever so slightly slower than the first. And this can be a problem if you've got a whole bunch of these flip-flops ganged together. They won't update at the same time. They'll sort of be like a ripple delay, which can really cause a problem if you want signals to update at the same time.